protector. Exploring the expanses of space to keep our planet safe. And all the species that call it home. I am a healer, giving doctors the vision to create amazing new cures. And using the heart's own magnetic field to diagnose itself. I am a guardian, searching a mountain of data to keep us safe when we travel. And a sea of people to find a lost child. I am a helper, powering autonomous machines that simplify our lives. Capture our greatest adventures. And make us whole again. I am a visionary, enabling taxis that don't need steering wheels. Those that don't need roads. I am even the composer of the music you're hearing. I am AI, brought to life by NVIDIA, deep learning, and brilliant minds everywhere.
Ladies and gentlemen, please welcome NVIDIA's Vice President of Accelerated Computing, Ian Buck.
Thank you. Thank you and welcome to GTC. My name's Ian Buck, and I'm here to tell you and give some perspective on where are we with AI and this industrial revolution. What are people doing today? And I want to give you some examples and help explain where AI is and where AI is going. To hopefully help you understand as you're here at GTC, as you're a developer, as you're seeing stuff happening around you, that you can understand, how can I apply this technology today? It's probably the number one question I get is, can you help me understand and demystify AI and figure out how it can help me in the kinds of problems I have? So hopefully this talk will do that for you. And of course, this conference is here for you as a resource to help you learn and enjoy and discover what it can do for you. But let's start with some perspective. Certainly, as we all know, we're at the end of Moore's Law. For decades, the IT industry was able to leverage Moore's Law that every 18 months or every 2 years, our computers just got twice as fast. We didn't need to think about performance. We didn't need to worry about the applications we were developing because in the next 2 years, I'm just going to buy the next server and it's just going to run twice as fast. That Moore's Law rule was actually a transistor rule. Every 2 years, we were getting twice the number of transistors. And CPUs just got twice as fast because smart engineers figured out ways to turn those transistors into faster, single-threaded execution. They invented things, larger caches, prefetch, probabilistic execution. By making one thread run faster and faster every year, the application just got faster. And then something happened. Around 2010, we continued to get more transistors, but we simply started running out of ideas. We maxed out on caches, we maxed out on prefetching, we maxed out on single-threaded instruction and parallelism, instruction throughput. And computers just stopped getting faster. Today, it's only about maybe 10 to 20% a year that we can run a single thread faster with every generation for every 2 years. Around that time, this new thing called GPU computing showed up. A programming model that was first invented for computer graphics. A typical video game might run a 10,000 line program or even a 100,000 line program on every pixel of the screen. A typical screen, this one's quite large, but in a typical screen may have 1 million pixels running at 60 frames a second on 100,000 lines, literally running 1 billion lines of code in a heartbeat while it refreshes, throws it away, and does it again. That massively parallel computation, which was done for video games, could also be applied to other use cases. In 2006, we launched CUDA and our first general purpose GPU computing platform, which we called CUDA. And since then, it has taken off. We're applying this new computing programming model, this GPU computing programming model, to all areas of science and computing. It started in HPC, it's expanded to deep learning, and I'm going to share with you some new areas where it's expanding into in this keynote. As a result, we've seen great success in the platform. We have over 1 million developers developing on our GPUs, using GPU computing. That's 10x in 5 years. Our CUDA, which is the main software people use to write code for the GPU, has grown to over 8 million downloads a year. That's 5x in 5 years. As a result, conferences like these where people learn to program GPUs has grown tremendously. We're 25,000 attendees worldwide this year. That's 7x in 5 years. And as a result of this new computing model, we continue to scale in computing. We have over 370 petaflops of computing on the top 500 supercomputers in the world, based on top500.org. In fact, the majority of new floating point operations that are added to that list today are coming from GPUs. The #1 supercomputer in the world, in the US, in Europe, all GPU accelerated. But let's talk about the reason. One of the reasons you're probably all here is about AI and what are people doing today in AI. I wanted to provide some perspective of where AI came from and the different use cases. If I break it down generally, you can think of AI in 3 different categories. First is image and image understanding. Second is language and understanding language and how we converse and understand the way we speak and the way what we write. And third is AI for decision making decisions from data. It all started with images. Back in 2012, a guy named Alex Krivetsky up in Canada was working on this thing that hardly anyone had heard of called deep learning. He developed a neural network that was deeper than anyone had tried to train before. And he was seeing some interesting results. The hard part was it took forever to train this thing called the deep neural network, literally taking months to train. It's a terrible way to get a PhD, to wait for one result for an entire semester and hope that worked. But he had heard about CUDA. He had heard about the kind of math that we were doing in supercomputing, the kind of math we were making available in our libraries and that people were doing everywhere. And he realized that math that he was doing for his deep neural network was the same math that we were doing at HPC. So he took 2 of our gaming graphics card, two GTX 570s. He downloaded CUDA off our website, and he ported his neural network software to the GPU, called it CUDA CovNet. This was probably the first GPU-accelerated AI framework. He trained his neural network in only a few weeks. He literally took it from months to weeks. As a result, he was able to iterate. He invented this network called AlexNet. It's named after Alex Krivetsky. He submitted it to a competition called ImageNet, which is a competition that's been running for years in the computer vision industry, a research area for recognizing, classifying images, and crushed the competition. While they were stuck at 71, 72% with traditional computer vision techniques, he came in at for years. He came in the 80s, and the year after that, pretty much everyone switched over to using AI. Today, AlexNet and the ImageNet competition, they've gotten so good they're superhuman. It's actually kind of hard. How do you run a competition where the results are actually better than humans? They have to get a panel of people to try to figure this out. And it's the result, they've shut down the competition because it's just superhuman. The first part of image understanding in AI, this is where it came from, was classification. It's a simple question. What is this a picture of? Is it a parrot or a Pekingese? A stop sign or a beach ball? Give me an image, tell me what it is an image of. Classification. Quickly, that's a interesting thing to understand, but of course the next thing you want to know is what's in the, like where in the image is the beach ball? Where's the dog? Where's the stop sign? We call that image detection. And today we have networks like SSD and YOLO that literally they take pixels in to the neural network and out is an XY bounding box and a confidence interval of where in the image is that stop sign, that car, that beach ball. The next step is not just bounding boxes, but I want to know exactly where it is. I want to do segmentation. I want to pull out every pixel that is the human or the stop sign in an image. The people that are doing great work in this is actually Facebook. So Facebook has, and Facebook Research has a network called Mask RCNN that does exactly this. It can take entirely inside an image and pull out the individual pixels. And if you look at that image, it's actually carefully able to detect and separate overlapping images. If one human is standing in another human, it's actually able to disambiguate which pixels are the first human, which pixels are the second human, who's in front. Very important task for segmentation, for pulling things out. So at this point, we're basically superhuman in image understanding in these three areas: classification, detection, and segmentation. And I'll give you some examples of applied use cases in a minute. The second area is language. Where AI was first applied to language was actually in sentiment analysis. Think about Twitter or product reviews on a website. I provide feedback that I like this football, I hate this football. I'd buy more, a positive thumbs up, thumbs down. Understanding the sentiment about products from interacting with customers in social media, in texts and tweets is critical for understanding whether or not this product is good, bad. Should I share this tweet? Should I not share this tweet? So doing basic sentiment analysis. Today, this was the first applications of LSTMs and RNNs for understanding language, strings of words, and the result of whether it's positive or negative. Very simple neural networks that are deployed today and deployed everywhere. The next logical step of language was obviously translation. There's over 100 languages on the internet, and if you have a social media website, if you are a search engine, if you're dealing with commerce and internationally, from Mandarin to English to Chinese to German, we need to be translating between all these languages to understand. There's many neural networks that are being used today. This is one of the challenges of AI. We're not in near superhuman levels of translation yet, but it's getting very good. In fact, Microsoft uses translation in Skype to allow a grandson in the US to talk to an Italian grandmother in Italy, and it'll actually do real-time translation for you. The third area with language understanding is auto-answer. You probably already experienced this today where your phone is already giving you some answers, or if you're on LinkedIn, it's suggesting responses. That's where it's actually reading your phone is reading the text and coming up with understanding it at a generic level and proposing a couple of answers. This simple form of auto-answer, of Q&A, is in production today, and there's many neural networks that are actually doing these kind of suggestive networks for simple responses. We have more work to do in language, and I'll talk about that a little bit later. The third area, and just in general, is decision-making. Taking data and applying it in a real-time use case. The first is search. Many websites are using AI today to take your search query, combine it with your profile information, with profile of information of people like you, and all the information that's been collected on the internet, and try to give that response in only a few milliseconds, typically less than 10 milliseconds. It's got to make a real-time decision. This is the bread and butter of the search engines of the internet today. And today, like Shazam is one example. Shazam is an app which you can get on your phone. It'll actually listen to the audio that's playing on the radio and tell you exactly what that song is. Oh, I like that song. I'd like to download it and buy it. That's an example of search, at least in the audio case. The second is recommender systems. There are many recommender systems to actually be done in AI today. One of the example is I'm going to a website for Amazon. I'd like to see what products I should buy. I go to Netflix, and it tells me what videos I want to watch. AI is being used for recommender systems today. The cutting edge work here is work in autoencoders and deep neural networks. So by actually being able to take all of the data from all of the users and the entire portfolio of movies or products, the millions that you have, and come up with real-time recommender systems. These networks can be very large because they actually have to comprehend the entire portfolio of products and all of the users on the website. And thirdly, and most recently, is anomaly detection, using AI for applications like cybersecurity. Today, modern viruses are not simple bit pattern strings that you can watch for. They don't have a single digital thumbprint. They're often self-mutating. They actually are designed to hide from those filters by changing their actual code, rewriting themselves in a self-modifying way, and propagating a very different bit stream that may have originally entered into your network. Companies that are deploying AI for this, Cylance is one of them, based in California. Cylance is a virus protection program, malware detection program, using AI to look for those kinds of digital mutations, looking for the patterns that match the access patterns, the interaction patterns, and the bit streams that match, does this fuzzy match with AI. As a result, Cylance was able to block 100% of the WannaCry virus outbreak that happened a few years ago, all running on GPUs in AWS. We're also working with the federal government. Folks like Booz Allen Hamilton and Accenture are looking at cybersecurity for protecting government data centers and using AI to look for anomalous patterns in traffic and deep packet inspection to identify and highlight to an operator when something suspicious is going on. Let me give you some examples of real-life use cases, but I've gone through the high level. One of the areas that images and image understanding can have a huge impact is healthcare, and particularly strokes. Strokes are a very scary thing. Every minute that your brain is deprived of oxygen during a stroke, you lose 2 million neurons. You lose 7.5 miles of neuron connections. They just die every minute. It's quite scary. And there's an expression in ER, stroke ERs, that time is brain. Now, we have, and for a good reason, because every minute we don't diagnose and treat a stroke victim, they're losing brain cells. We have a tool for understanding what's happening inside the brain. It's called CT. CT scanners actually take x-rays of the head and will produce images for radiologists so they can identify when there's hemorrhaging, bleeding in the brain, or stroke, where we have oxygen loss in the brain. Working with folks at the Wexler Medical Center at Ohio State University, they're actually developing a radiologist tool to help them prioritize and find the most critical cases immediately. One of the challenges in radiology is that there's no shortage of CT machines anymore in the US. In fact, doctors proactively prescribe them if they can, because they know how useful it is to see inside the human body. But the workload of the radiologist is extreme. According to the Mayo Clinic, a radiologist usually processes about 8,000 images every day. That's a lot. In fact, 40% of the CT scans are categorized requiring immediate attention, a stroke victim. That's a lot of workflow. By researchers and PhD Dr. Erdahl at Wexler Medical Center is actually developing an AI tool to help radiologists prioritize that queue. Which of these scans actually is one that needs immediate attention? To flag it to the radiologist, to do the diagnosis, to get that person into the ER to treat that stroke victim. They've developed a hemorrhage algorithm and a stroke AI algorithm by applying what is a simple, actually, GoogleNet image classification network. This is not a difficult science, just looking at classifying all the medical images that they have and providing that tool to radiologists can truly save lives. Another place where image understanding can add a lot of value in AI is actually in preventative maintenance. We're building amazing machines. If you look at an oil rig that may be sitting off the coast of Alaska or in the Gulf of Mexico or up in the Nordic Sea, these are incredibly harsh environments. These are incredibly complicated machines that need to stay working for a long time. A company called Avitas, which is a GE venture company, is actually using drones to help monitor and observe and do preventative maintenance on our oil and petroleum infrastructure. Instead of having a human have to walk and scan this entire complex, potentially in a very dangerous and hostile environments, we can use drones. This semi-autonomous drone is actually equipped with an IR and color camera. It can autonomously fly around the oil rig along the pipelines, and it actually has a neural network which is automatically trained for doing things like detect corrosion, look for paint breakdowns, insulation breakdowns. Using the IR camera, they can look for heat distortion and things like concrete sprawling, where water is leaking into concrete and it's breaking down. It can, by feeding this video back to an operator, which has a GPU workstation, it does real-time bounding boxes. So this is, again, detection, placing it around areas where it's detecting one of these early failure indicators. Not only that, it does classification as well. So it can tell you if it's level 0, level 1, level 2, to give an indication of the severity of the issue. By deploying this technology in preventative maintenance, they actually have done a 25% decrease in annual facility inspection costs. It's cheaper to do it this way. They've increased their equipment uptime by 15% to keep the machines running longer. And it's a 25% faster turnaround on inspection. By finding these issues early, where they're much easier to treat, it's cheaper, faster, and frankly, a hell of a lot safer to do it this way than wait for the infrastructure to potentially fail, or God forbid, leak. But a basic application of image processing, image understanding, using networks that are readily available today, even with open source software. But let's talk about decision making. This is an area that's actually been around probably the longest. This is where we take all of the data that we've been collecting. For the last decade, we've been in the era of big data, which is, as far as I can tell, collecting a lot of data and trying to figure out what to do with it. We've been applying traditional machine learning. If you look at what GPUs accelerate today, we started in scientific computing. We're in the era of deep learning now, and I've given you some deep learning examples, but there's a huge amount of computation that's happening today in traditional machine learning. In things like retail logistics, finding out which warehouse should I ship this product to this home address to maximize delivery, maximize the happiness to my end customer, to keep my shipping costs down, to reduce my gas bill, or in some cases, reduce price. I may be willing to trade off one day and get the product a day later and save some money, get a cheaper price. Because I don't necessarily need it tonight. I can wait for Saturday. Folks like Walmart are using machine learning to do that. In additional entertainment, the kind of videos you want to see on Netflix or the products that get delivered to you, they use machine learning to actually just do those traditional recommender systems. And of course, finance. Finance is full of information to calculate risk, to decide loans, to understand their portfolios. Machine learning has been a tool for a very long time. This is a huge market and a huge field. It's one that's been it's also highly diverse. It's full of open source software like NumPy, scikit-learn. It's full of algorithms like gradient boosted trees, k-means clustering, a long laundry list of regression algorithms. It's actually quite difficult to get your arms around it. For the last 2 years, NVIDIA has been investing and developing technologies to help attack this market, to make it run faster. And I'm excited to announce that we've developed a new open source software stack for accelerating traditional machine learning. This ecosystem, accelerating machine learning, is about accelerating its data preparation, model training, and visualization. We call this software Rapids. Rapids is an open source accelerated data science set of libraries that's designed to work with all the open source software out there today, from scikit-learn to Python to Spark to NumPy. It consists of a couple of core libraries, the first being a library called cuDF. DF stands for data frames. Most of the data that's being processed in machine learning is captured in data frames. This was invented by the folks at Spark. And we have an accelerated data frame manipulation library, which accelerates loading, filtering, manipulation of data for preparing it for model training. It's compatible with Apache Arrow, which is the standard now for machine learning data frames. Second, we have a library called cuML. cuML is a basket of a long laundry list of different GPU-accelerated machine learning libraries. They include things like k-means clustering, KNN, random forest implementations, regressions, gradient-boosted decision trees. I'll show you some examples in a minute. In addition to that, cuGraph. cuGraph is a graph analytics library that's for seamlessly integrating in for graph processing, which again is another application of machine learning. This all works and is compatible with Apache Arrow, which is the standard machine learning data frame data exchange formats, and is also compatible with Dask, which is a distributed scheduler for scheduling and scaling up machine learning across multiple GPUs across multiple nodes. The machine learning workflow is actually very challenging. You have to take huge amounts of data and do extract, transform, and load. This is the bane of a data scientist, being able to take all of the data and prepare it so that we provide clean data into our training. There's an expression in data science is garbage in, garbage out. If you give it crap, it's not going to work. So we have to clean that data and structure it to provide cleanly structured and filtered data to our training pipeline. Once we're in our training pipeline, we have to do the final step of data preparation, run it through a model training, one of these regression analyses, and then iterate to refine the model to get it to a certain level of accuracy that we can deploy it for inference. At the same time, we need to be visualizing the data and providing the data scientists those insights. With Rapids, we've accelerated this whole computing pipeline, and also working on the inference step next. But let me show you what the visualization looks like. This is a picture of mortgages. This is 140 million mortgages, which is captured from 2006 to 2016 from Fannie Mae. Fannie Mae is involved in about half of the US mortgages, worth about $1 trillion. So understanding mortgages and mortgage risk across the US by region is critically important. This is 10 years of data. The red indicates areas of high risk, geographic, where the credit scores in those mortgages, based on a gradient-boosted tree algorithm, have potential for default. The blue is areas of less risk. We can also, with this visualization, in real time, show you how much unpaid debt there is by region. Not surprisingly, San Francisco is one of the most expensive places to live. I get the joy of that. Actually has an enormous amount of debt, but it's blue because the credit scores there tend to be high. It's a low-risk area for default. As a data scientist scrolls along, you can see other parts of the country which may be a little bit more concerning or higher risk. This is some of the suburbs of Chicago, where we still is a very expensive place to live. It's a city, basically, but the credit scores are more risky. This is an area where a mortgage company can go in. They can send their local team responsible for that area to proactively offer refi agreements, maybe give them better terms. It's better to make those loans a safer loan, perhaps make less money, but rather do that than have them default. This kind of real-time interaction was never possible before. This data scientist is in real time doing group buys and joins and filters on 140 million mortgages across the entire US. This is a half a terabyte of mortgage data, all sitting resident in GPU memory, all interacting in real time, allowing the data scientists to really explore and understand their risk using traditional GPU-accelerated deep learning. To give you some perspective of the performance deltas, if you tried to do this workload on a CPU, on 20 CPU servers, it would take you almost 2 hours to just do the extract, transfer, to load, just to get the data into memory and process and pre-filter it. On a GPU system, this takes less than a minute. Then to train the gradient-boosted decision tree that you visualize there, on 20 CPU nodes, it's almost another hour, where on a GPU, we can do it in about 2 minutes. End-to-end, the whole solution on 20 CPU nodes is about 2.5 hours. On a GPU, we can do it, or almost 3 hours. On a GPU system, we can do it in just 3 minutes. And amazing, this whole thing happened on a single server. On the right there is the DGX2 server. Inside of that box is 16 Tesla V100 GPUs, a half a terabyte of GPU memory, all staying resident, interacting in real time on top of the Rapid stack. And the best news is it's still a GPU. It's still rendering and doing all that rendering on the NVIDIA GPU as well, so we can capture the visualization workflow as well. This is going to transform traditional machine learning. In the expo hall, right after this keynote, I encourage you to walk around and explore and ask questions. We have some of our Rapids partners here. We've been working with the entire open source ecosystem for machine learning, in addition to the enterprise data science platforms from companies like IBM, Oracle, SAP, and SAS. The startup community, which is doing all sorts of amazing disruptive technology and applying machine learning to new use cases. And even the deep learning frameworks. They recognize that there are portions of their workflow which AI is suited well, but also traditional machine learning can add value. And integrating Rapids into frameworks like PyTorch from Facebook or Chainer, which is popular in Japan. And of course, Rapids runs on every GPU server from every OEM, and we've been working with our storage partners because machine learning and data are inherently linked, and making sure that we can stream the data real time and be uninhibited by the storage infrastructure by working with all of our storage partners. The great news is this is all free. We've placed this, you can download it today from rapids.ai. Get these containers, get these libraries, use them inside of scikit-learn seamlessly, and start exploring how machine learning can be accelerating your workflow with GPUs today. And I encourage you to explore the show floor and see how they're using it today. Okay, let's go back to AI. We talked about today's applications of image classification, detection, segmentation, language models for sentiment, all the way to auto answer, to decision makings for search, anomaly detection, and recommender systems. Where are we going? In images, it's interesting. We're going from understanding the images now to manipulating them, to improving them, to making them better, to creating images. I'll give you some examples of image enhancement, but then we can go a step further. In some of our drive and autonomous vehicle work, we're actually using it to do image generation, creating scenes using AI from high-level, simple renderings to filling in the holes by having AI create scenes for us. In language understanding, we're going from the simple auto answer, which is on your cell phone, to actually having intelligent search queries. You know, I believe the future, instead of trying to understand things by searching for them on the web and clicking on a link, increasingly, if you haven't noticed, the browsers are starting to answer the questions right for you. Give you the answer that's already on Wikipedia, but instead of having you click and read about it, it just tells you the answer. This is an intelligent form of question and answer and how we're going to be interacting and searching for things on the internet. The browsers may just tell you what the answer is and help you understand it. That requires a good understanding of what is actually being asked. Not the actual words, but the meaning, which obviously is going to be personalized to you, and understand the meaning from all the web content, not just a copy-paste from what's on a web page, but create an intelligent answer on the result. That is called a much more intelligent question and answer understanding, which is how we're going to interact with browsers in the future. Take that a step further, we have intelligent chatbots. This obviously is a competitive and exciting part of the market, where how we talk to our devices is not going to be necessarily through keyboard, but with our voice. Whether it be that hockey puck in our kitchen counter, or driving in a car and talking, because this is how we want to naturally communicate with the cloud and ask questions and get information. There's a lot of people working on intelligent chatbots today to make that a reality. And finally, in decision making, there's all sorts of, I'll talk about robotics and the cool stuff that's happening there, and planning. And how robots can become more intelligent based on AI. This is an advanced form of decision making. And then you go all the way to autonomy and self-driving cars, which is combining all of these areas to make self-driving cars a reality. Let's first talk about enhancement in image. Some of the work here is amazing. This is a example of super resolution. This is using a neural network called a UNet, which is a form of autoencoder which has a bunch of skip connections. It's some of the, actually it's a over, I think, 2 gigabytes in size. It's one of the largest neural networks out there. It was trained on scaling images. It's actually a really simple training process. Take an image, downscale it, make it pixelated, show the neural network what the picture was before and what the downscaled one was. It learns how to now upscale pictures. The input to this neural network was this pixelated image of a waterfall over a leaf and a rock. The output of the neural network was the picture on the right. It's actually doing image reconstruction and enhancement to take a almost uninterpretable image that's pixelated in low resolution to make something beautiful on the other side. Another example, you can look at the hand and how clean that edge and defining those little edges are. This is basically the magical enhance button that we've always seen in Hollywood and AI, where enhance. Neural networks can do this today. It can take a picture and just enhance it by being trained on what a low-res image is to a high-res image. And in medical imaging, for those of you in the front, maybe you can tell a little better. You can take a low-resolution pixel image. We can do domain-specific training. We can give it a bunch of X-ray images at low-res and show what they look at high-res to teach an AI how to take a pixelated image or a low-res image on the right and enhance it specifically for medical imaging. But not just images. What about 3D? Segmentation, classification can be applied not just in 2 dimensions, in 3 dimensions. For healthcare, this is the next step in medical imaging. Today, they do some of this. This is a CT scan of a human torso. What CT is actually an X-ray machine that takes an X-ray, and they turn the CT to take another X-ray, turn the CT, take another X-ray. And they use a technique to reconstruct those 2D pictures to create a 3D volume. This has been around for a while. This is using 20 CPU servers. It took about 30 seconds to compute the X-ray, to turn the X-ray into 3D, to create a 3D volume. This is pretty good. We can see the bones clearly, although the insides are a little bit blurry. If we apply AI to this problem and apply segmentation, we can actually pull out the individual organs. And then we take it a step further, we can do real-time ray tracing on this to actually do full reconstruction. So what we're left with which was a fuzzy, blurry image of the inside, we can actually provide a real-time cinematic rendering through AI segmentation and filtering to real-time ray tracing to recreate what's inside the human body. This is done in real time, running on this CT data, and doing real-time ray tracing to do that reconstruction. Now look at the details from the left, which is basically a blue blob. We can actually see the heart, we can see the lungs and livers, and now we can explore the windpipe and all the bronchial tubes. This is all done on a single GPU system, and sort of the future of medical imaging. It's really, truly amazing. We're going to be in a world of Star Trek where I can be scanned and zoom into my own lungs and share with the doctor, and he can show me what's going on inside instead of looking at a fuzzy blue picture. Thank you. We call this software Clara. It's available today on our NGC Cloud registry, again, freely available. We're working with all different medical devices, not just CT devices, but MRIs, ultrasounds, PET scanners. This also can be applied to cryo-EM, which actually just won the Nobel Prize a few years ago in high-resolution imaging, for doing the high I/O speed sensor processing, the image reconstruction, AI-based classification, real-time ray tracing, all available in the Clara platform. The next step in healthcare is understanding the data, and as particularly genomic data that's in healthcare. Healthcare, if you can look at all the genomic data that we've been collecting, all the electronic medical records, all of the Fitbit and health sensing data that we've been collecting, there's a treasure trove of information. What we need to do now is figure out, in all of that sea of data, how can we use that to apply it to do early diagnosis of disease, whether it be heart attack, heart failure, cancer, or many of the other life-threatening diseases. That's probably sitting there in our data. We just haven't figured it out yet. NVIDIA is announcing this today that we're partnering with the Scripps Research Institute to actually start down this path. We're going to take our data scientists and some of our infrastructure and work with data scientists at the Scripps Institute and the data they have on biometric data and genomics data to start looking for patterns in this. AI loves data. It's designed to process and look for patterns that were basically unfound before. And by going through historical genomics and biometric data, we're looking for those needles in the haystack where we can identify this stuff early and make a real impact. Let me switch to another application of AI that's actually coming online, which is agriculture. You wouldn't think agriculture would be a place where high-tech AI would make a difference, but it truly is. On the right-hand side, we have a machine from Blue River Technologies. This is a company owned by John Deere. They call this machine LettuceBot. I think that's cool. Each of these little devices in the front of this tractor has a little camera. And as the tractor drives by the row of lettuce, that camera's looking down at the ground and trying to figure out, is that little sprig of green a piece of lettuce or is it a weed? And if it's a weed, as it scrolls by, it does a little squirt of pesticide. Using AI and image recognition and segmentation, it can very quickly identify the difference between a lettuce and weed, and as a result, do precision pesticide. Instead of spraying this field with a plane and including the food, we can only spray it where there's a weed. They've actually been reduced pesticide use by 90% using AI. They also increased the yield of the field by 10%. Today, LettuceBot is actually deployed on 10% of the lettuce crop in the U.S. today. And they're looking to expand that to soybean and cotton and other areas. Cray Technologies is building drones to help monitor the crop health. By taking a drone and having it autonomously fly over the field, by having a camera looking down, it can tell if the plants are under stress, underwater, under-fertilized, using classification techniques to give the farmer an area where to and thoughtfully deploy more water or more fertilizer. Cray actually is interesting. You can do this easily with multispectral cameras, which are very expensive devices, and very expensive rigs, which are not necessarily available around the world. They're actually using low-cost sensors and commodity drones to try to do this with regular RGB cameras that you and I have today on our cell phones for doing this. And the third is actually looking at the picking problem. I didn't know this, but apparently strawberry fields are particularly onerous. You have to pick a strawberry field every 3 days. It's not like a crop that just grows and pick. You have to constantly be repicking the entire field every 3 days. There's a company in Europe which has built Agribot that actually each of these little arms has a camera, and it's using segmentation and identifying which strawberry and its stem and very precisely picking the strawberry right at the stem. Interestingly enough, it also never touches the fruit. It only grabs and snips just the stem, because the fruit is where, if you grab the fruit, it would potentially spread disease. That's where the mold and disease is. So by doing that precision picking, it can actually prevent the field from spreading infection or mold. They're starting with strawberries because it's a small and select use case, and it's an onerous crop to deal with, having to pick every 3 days. Very cool. But we can take this a step further. One area where AI can have another meaningful impact, and is research going on right now, is in disaster relief. We just came through Hurricane Michael, which hit Florida. But any one of these disasters of hurricanes, typhoons, or tsunamis immediately wipes out a city's infrastructure. There's no power. There's no cell phone. There's no police driving the streets because the streets are blocked or flooded. As a nation comes to the aid of a city struck by natural disaster, that first 48 hours is critical. Knowing where to spend and find and save lives is incredibly challenging because you literally don't know what is going on. The best we can do is fly over these areas with helicopters, airplanes, potentially drones, to identify and find areas where people need help. Is there someone stuck in that bus that's been flooded? Is there someone trapped underneath that underpass? Are people floating down a stream? Are people gathering in a certain area and need help or rescue? Or looking for people in water? The first 48 hours are critical. We have, NVIDIA is announcing today we're partnering with Carnegie Mellon and the federal government to try to attack this problem. We're taking our data scientists, our infrastructure, working with Carnegie Mellon and the federal government to provide an AI accelerated solution to help quickly assess where we need in disaster relief and human assistance in the first 48 hours of a natural disaster. This is an area where I think we can make a huge impact in saving lives. Thank you. The next problem, and I'll in AI, is autonomy and self-driving cars. This, you have a combination of both image understanding, decision-making, and even language and interactivity. This is NVIDIA has been working on this problem for a long time. We sell a self-driving car platform to all the automakers. We developed a self-driving car technology ourselves for them to go integrate into their platforms, their solutions, their vehicles. This is our test car. We call it BB8. As you can see, it has a bunch of cameras, LiDAR, ultrasound sensors combined in a sensor package. It all runs on our Drive platform, which is a AI car computer you can see on the right. This car computer has to do fairly complicated sensor processing, sensor fusion, make sense of multiple sensors that understand things differently, combine that information. It then needs to do full perception of what's around the car. It needs to do mapping and localization to understand where the car is on the road, where the car is on the map. It has to do all sorts of situation understanding to know when it's safe and where to go. And of course, do path planning and task planning. And of course, this is a safety critical system. It's driving us around, so there needs to be redundancy and diversity in that processing to make it safe. We've been working on this problem for a long time. There are many neural networks used in self-driving. This is a sample of some of them that we use, that we've been developing. So the first is perception, developing, identifying cars and different vehicles. Free space perception. It's a form of segmentation. An image comes in, we need to know which pixels are drivable roads, which pixels are not drivable. Our free space perception network actually does that. As you can see here, it's drawing an outline of where is it safe to drive and not drive. Distance perception, understanding how far something is. Is it coming at you? Is it going away? Its speed. Again, we can use AI to predict and understand the motion of objects around us, obviously critical. Things like understanding weather. Is a road slick? Is it wet? Is it icy? Is it dry? Is important. And then many of these devices have LiDAR or other kinds of sensors. Being able to take a point cloud from a LiDAR and reconstruct the world around it, we use AI for that. And then taking all that information both from the LiDAR and the cameras to localize the vehicle. We have high-resolution maps of most of the major roads in America, but we have to put the car on that map precisely so we know where we are. We use, again, AI to do that localization. And then finally, path perception and scene perception, understanding where the lane is, the objects in front of it, where is it, and where do things turn, and signs. So let me give you a simple example of how we develop these neural networks. We do all of this actually before we ever hit the road in simulation. A simple simulation is emergency braking. Many of you probably have cars that can stop themselves if you're about to hit something. There's actually a test track where car companies are required to go and test against dummies. The dummy looks just like that. It's a little cardboard cutout that's walking across. They've been horribly mutilated and hit many times. So it's a lot nicer to the dummies to do this in simulation. The other nice part about doing it in simulation is that you can test not just these dummies, but all different kinds of cars. Cars you would never want to hit because it would cost you an arm and a leg to hit them. You can test in simulation. We do all of this emergency braking simulation in our own infrastructure. That allows our data scientists to take the camera input, test this infrastructure, and make sure it works. But this is just emergency braking. What about the whole self-driving stack? So we also use simulation to test our self-driving vehicle. We try to create the most realistic rendering of the world around you. This is actually a simulation. This is not real. We've taken high-resolution maps, which we got from TomTom, and reconstructed the 3D world. This is actually a road in the Bay Area, and placed our vehicle in that road, running the actual neural networks that would run in the real car and seeing how the car behaves. Using a hardware-in-the-loop method, we actually put the entire drive stack running on the production hardware, and the simulation provides simulated input to the cameras, run the real stack on the real hardware. The output is torque to the steering wheel and pressure on the gas pedal. By doing this hardware in the loop, we can actually test the vehicle in a virtual environment where it's at least 100% safe for humans. We can do all different kinds of weather, all different kinds of scenarios that we would never want to actually potentially see in the real world or would ever risk testing before we ever take the car out in the actual road. As you can see, this is the test track is entirely done in simulation in computers. The GPU is running the neural networks, the GPU is doing all the rendering, the GPU is making all the decision making. And it allows our data scientists that are developing this software stack to test in real time. Well, I'm pleased to announce that this has been very successful for us, and let's show what this car can actually do on the real road. So this is a test run of our AGX Pegasus running in this car. This car was running fully autonomously in the Bay Area. If you're familiar with it, it's 280. Emerged onto 92. It then changed lanes, got onto 101, came back down to 85, which is a real pain. And if you've ever done that, and then comes back around to 280. This is what the car sees. This is what the AI is seeing. We're doing real time. You can see the free space calculation, all the neural networks running in parallel. As it's driving down the road, it's avoiding other vehicles. You might recognize some of the scene from the earlier simulation. It's able to do a 3D bounding box around every vehicle, knowing where it is. When it cuts you off, it knows when it brakes, it turns red. It's tracking speed. It's tracking lanes. It's doing multiple path predictions to figure out where to go, and has to do things like these merges right there to stay on the road. We need a neural network to watch the driver. The driver cannot lose concentration. They are responsible if they ever have to grab the steering wheel, and it will alert the driver if they're not paying attention.
What's the weather in San Francisco now?
The weather is 67 degrees and cloudy in San Francisco.
How about tomorrow?
There will be partly sunny skies with a high of 69 degrees in the lower, 58 degrees in San Francisco tomorrow.
Merging onto 85, very difficult. It's actually a left-hand side merge, not a right-hand side. I'm not sure an autonomous vehicle counts as a passenger for HOV, but it's cool. Get stuck behind a garbage truck here. It happens. There you go. 50 miles, no hands. This car we brought to DC. You saw this picture in front of the Capitol. It was taken the other day. We have it out here. I encourage you to see it, check it out. This is some of the most fun areas and applications of AI, which is going to change the way we drive, the way we use our roads, the way will revolutionize the auto industry. As I mentioned, simulation is a huge part of how we develop these AIs. And in fact, it's kind of how we feel we need to validate that these AIs are street-worthy. How are you going to give a car a driver's license? You have to prove that this car can be safe. Though we can maybe test millions of miles, we really want to test billions of miles to validate that the self-driving solution is actually is working in all different scenarios. We believe that simulation, not just for development, but for validation, is a critical part of that process. At NVIDIA, we have 4,000 GPUs in our DGX supercomputer, which we use to test all these different kinds of scenarios. And the good part about it is that this whole software stack and this infrastructure is available to you. The same servers, the same GPUs, the same AI software that was used to develop self-driving car is available in open source. It's available in our NGC container registry. And the servers, whether you purchase it from OEMs, you rent it in the cloud in AWS or elsewhere, or you purchase it directly from NVIDIA for DGX, is available to the rest of the market to develop those AIs. In fact, for the federal government, we're pleased to announce that Red Hat will be supporting DGX as an OS provider and support provider for DGX systems, Red Hat being the leading OS provider and certified for the federal government data centers. We're pleased to provide that on NVIDIA's own DGX platform, our station in DGX1 and DGX2 systems. Well, in the last 90 days, this is one of many GTCs that NVIDIA has done, and we've announced many different products. I didn't have the time to go through all of it here. We have entirely new GPU architectures called Turing, which is optimized for real-time ray tracing for visualization and gaming, and also for deploying AI inference at scale with the Tesla T4. We've refreshed our entire software stack. Our container registry now has complete new software stacks for science with our CUDA platform. We have containers for all the major AI frameworks that have been optimized for NVIDIA GPUs for training your neural networks. For AI inference and deploying deep learning at scale, we have new inference software stacks, including the TensorRT inference server for deploying all these different use cases I talked to in containers. And now with machine learning, we've rounded out the scope of what today's computational data centers is doing, whether it be science and simulation, AI and deep learning, or traditional machine learning. All of this software is available and freely available on our NGC Cloud container registry, or build it yourself from GitHub, or download it from rapids.ai. And finally, we've also refreshed our embedded stack. I talked about our Drive platform. That same platform, which we call AGX, is available for robotics, for medical devices, and autonomous vehicles. It comes in a variety of different sizes of different horsepower based on the level of autonomy or intelligence needed in the embedded device. So to conclude, I want to thank you. You're now in the age of AI, where every industry will be enabled, empowered, and by AI, whether it be the autonomous vehicles that I showed you, robotics, to industrial applications for predictive maintenance, for infrastructure, for studying our roads and infrastructure and improving and finding the potholes and tarring the road before they ever happen, to applying to finance and improving risk and better outcomes for homes and mortgages, to media and entertainment for giving you the best recommendations, to the internet and cloud service providing, to how we talk to our devices, how we talk to our phones, how we communicate with our computers and ask questions. AI is going to be used for revolutionizing scientific research hand in hand with simulation by looking at the data that's being generated and helping scientists make those new discoveries. And finally, I think the industry that's going to be most impacted is healthcare, truly saving lives by using AI to dig through our medical data by better, more accurate processing and timely processing of critical life-saving applications for medical imaging and CT. This conference is about helping you understand how you can apply AI to your problem. I've purposely walked through a bunch of variety of examples to help you pattern match. The great news is this whole field and industry is very open. It's built on open source software. It's available on GPUs everywhere. And we have lots of people in the expo hall who can explain further about how they're using AI or machine learning to improve their industry and their problem. I hope they inspire you to discover the next step for how you can apply this technology to your problems, your agency, or your industry. Thank you very much, and enjoy GTC.